So, welcome to this class. So, just briefly, in the last class we talked about the resolution, we talked about the numerical aperture, the importance of Rayleigh's criteria to determine the resolution of any microscope, and we also derived some basic equations related to the numerical aperture and also the how it depends upon the minimum distance which can be resolved by any lens or the microscope. Okay. So, x, what we got is x is equals to 0.61 lambda divided by n a here n. Okay. So, this is the minimum the formula for the x to be resolved by a microscope which is related to the microscope resolution. Now, what we will do is we will talk about two important aspects. One is depth of field and another one is depth of focus. Okay. So, first we will talk about the depth of field. So, the image is in focus when the object lies in the appropriate plane. Okay, this is very important here, appropriate plane. Okay, so if the object lies above or below the plane or equivalent part of then what will happen is the equivalent part of the object will be out of focus, Okay. So, the range of positions for the object for which what we call is a depth of field is the range of positions for the object for which there is no change in the sharpness of the image. Okay. This is known as depth of field. Okay. So, here I am showing you a figure where you can see that this alpha is here wrong. So, alpha is this much only. Okay. So, here you can see that this particular plane is the optimum focal plane, okay, and your beam is converging onto the sample surface, correct. Now, and the height h, this is the height which is called the depth of field, okay, and this height will be calculated by will be estimated by assuming that there is a diffraction effect that will limit the resolution of this particular value d1, correct. The sharpness of the image will not any difference within the range h. So, the depth of field, the h is the distance or there is the distance centered on the plane of optimum focus where the sharpness of the image does not change, okay. And if you see the simple trigonometry, if you plot this particular triangle, okay, then this is called h by 2, okay, and this is called x by 2, this particular distance, fine, at this distance. So, you can get that the tan alpha is given by x by 2 divided by h by 2, which is equals to x by h, and if it is in the medium or any medium, air or some other oil medium, you have to put up a refractive index mu. fine. So this is your tan alpha. Now if you compare this particular formula with this, okay, then you can put H is equals to 0.61 lambda divided by n or mu sin alpha into tan alpha, okay, and this particular term is nothing but the x, the minimum distance which can be resolved, okay. So here you can see that the depth of field which is H increases by decreasing the convergence angle, and this convergence angle is controlled by objective aperture, okay. So this is how the definition of depth of field. But the problem is, if you lower the alpha, decreasing the convergence angle, it will have a direct effect on the resolution. So it has to be a optimum value of alpha to be chosen for the for the optimum depth of field in any microscope, okay. So instead of light, if you use the electrons for the imaging, then it actually improves both resolution, because your lambda is very small, and also the depth of field, okay. So it means that if you use an electron source as for the imaging, you will have a high resolution because of the lower lambda, and the depth of field will be very good because your alpha will be minimum or lower, okay. So this is called depth of field. Now we will come to the depth of focus, okay. Now what is the depth of focus here? As I told you, depth of field is the range of positions for the object at a particular plane where the image is sharp. But what is the depth of focus? Depth of focus is the range of positions of the image plane for a fixed position of the object, okay. So it is a range of position at which the image can be viewed without appearing out of focus for a fixed position of the object, So example, by so you know that magnification is given by V by U, correct. Now if you differentiate this equation, then what we will get is dV by du is equals to minus V square by U square, which is equals to minus m square, okay. So dV is equals to minus m square du. Now what does it mean? dV, the effective shift in the image. So dV corresponds to the shift in the image, because V is the distance of the image from the lens. So dV corresponds to the effective shift in the image position in related to the du. So the change is change in the position of the object, okay, and this is directly related to the square of the magnification, okay. So du is the depth of field calculated by above, and the equivalent depth of focus dV. So depth of field can be calculated by this particular the range of position for the object, and dV can be calculated by this formula, where it is usually bigger by factor of m square. So it means that at higher magnification the depth of focus is large, okay. So this is called depth of focus. Okay. So, now we have gone through the just basic related to the depth of field and depth of focus, and these are very important terms when you are using a microscope to see that your image is not is sharp enough, correct. Now, next we will talk about the aberrations. So, in any lens system, either it is a electromagnetic lens system or either it is optical system, there must be aberrations related to the lens, okay. And these aberrations directly affects the resolution, the depth of field, okay. So, usually in the microscopes we assume that all the lens systems are perfect. Okay. It means that perfection means throughout the lens system. If you talk about this lens system, if a light rays falls on this particular lens system, then the focal point will be same at each position of the lens system towards a one point, okay. So, it creates a single image without any aberrations, but the lens aberrations you cannot avoid, okay. So, there are three basic lens aberrations. One is chromatic aberrations, the second one is spherical aberration, the third is astigmatism. What is chromatic aberration? As the name suggests, it is a if for example the light has a range of wavelengths with different colors, correct. So, if a range of wavelengths is present in the light, okay, and your lambda has a certain range in the light, correct, and each lambda value, lambda 1, lambda 2, lambda 3, their focal point will be different after it passes through the lens system, okay. So, a range of wavelength is present in the light and arise because a single lens causes light to deviate by an amount depending on its wavelength, variation in the wavelength, okay. So, it means that the lens will have a different focal point, corresponds to different lambda. This may be lambda 1, this may be lambda 2 focal point, and it is so this is the chromatic aberration. Now, you will have a certain disk of confusion within this range of wavelengths, okay, corresponding wavelengths, the focal point of those wavelengths. So, this chromatic aberrations can be minimized by using different lenses with different refractive indices, so that it will eliminate the variation in the wavelength by using the filters, okay. So, or you have to in a transmission electron microscope, what we can do is you can use the source monochromator source to minimize the chromatic aberration. Now, the second aberration, common type aberration, is the spherical aberration, okay. So, this is because of different path lengths of different rays which are passing across the lens system. So, it means that if a ray passes to this location and if it passes through this particular location, then the focal point for this particular ray and the focal point of this particular ray will be different, okay. So, the portion of the lens farther from the optical axis brings rays to a focus near to the lens than does the central portion of the lens. So, if a ray passes through it, the focal point will be here, but if a ray which is near to the optical axis, the focal point will be somewhere here, okay. So, this is the first position, second position. So, you will have this disk of least confusion which is due to the spherical astigmatism, okay. So, spherical aberration spherical aberration can be minimized by using apertures, okay. So, apertures means you can use the aperture so that the rays which are away from the optic axis can be avoided to create the image. So, you will come near to the close to the optic axis. The third aberration is called astigmatism. Astigmatism, it is nothing but the object points the object points of the optical axis. The object point of the optical axis, okay, if so, it means that the light rays are focused at different locations. At different locations, if you take about the horizontal and vertical planes and vertical planes, it means that the rays at from this position, it will have a focal point of here, okay, and the rays which are in this position, which is this is vertical plane, this is horizontal plane, the focal point will be somewhere else. This is called astigmatism. Okay. So, here also astigmatism you can minimize by using, usually in the transmission electron microscopes, we use stigmator coils. Okay. So, to actually remove the astigmatism from the image formation or the aberration, correct. So, these are the basic types of 3 types of aberrations here, correct. Now, if you compare these aberrations based on what source you are using it, okay. So, if you compare these aberrations based on either electron as a source or either as a light as a source, okay. So, the light, as we can see that the wavelength is between 400 to 700 nanometers lambda. For the electrons, the wavelength is very low, it is around 0.001 to 0.01 nanometer. Your lambda is very low in the case of electrons, okay. And these usually used in the TEM and SEM as electron source, these are usually used in optical microscopes, okay. So, the electrons, they have a very small wavelength, they usually scatter by gases very heavily as compared to light. So, usually the optical paths, whatever the electron, wherever the electrons are used, the path, the optical path is usually evacuated to a pressures, to a very low pressure of 10 raised to the minus 10 pascals or 10 to the minus 7 atmospheres, okay. So, in for the electrons, the lenses which are used in SEM or TM, those are called those uses magnetic fields, okay. So, those are called electromagnetic lenses, okay. So, here as I told you that this is in the vacuum, the very low pressures. So, here usually the mu refractive index is 1, is related to 1, and in electrons the alpha is very small. So, here what we can do is we can assume sin alpha is equals to tan alpha, okay. And so, therefore, if you see the theoretical resolution R1, we can put it as a 0.61 lambda by alpha, okay. So, if your lambda is very small, around 0.0037 nanometer, which is typically achieved when you use a 100 kV voltage, the potential difference. I will come to that how to generate these electrons, okay. Then your alpha is, if it is around 0.1 radians, which is around 5 degrees, then your R1 achieved is around 0.02 nanometers. This is the ideal resolution which you usually will get by using a lambda of this much value, 0.0037. But the problem with the TM is you cannot achieve this ideal value. As I told you before, there are certain aberrations which are related to chromatic aberrations. Okay, these are spherical aberrations and astigmatism. Astigmatism can be corrected fully by using stigmator coils. Chromatic aberrations, you can use monochromators. Okay, so the range of spread in the lambda or the energy spread will be minimum. Okay, spherical aberrations, as I told you, you can use the apertures, that is by restriction the electron to the path near to the optical axis. Okay, so usually the spherical equation, so you have a R1, so you will have a disk of confusion or the radius which is R2, the minimum distance, which is equals to CS alpha cube. Here the CS is the spherical aberration coefficient, and here the alpha is very low values. You have to select very low values by using apertures. But if you use the alpha lower values, then usually you are affecting the resolution. So there should be a optimum value of alpha to be chosen, so that it will be balanced between the resolution. Okay, it should be. So your actual R is equals to R1 plus R2. Fine. So this is the just a mathematical equation where you can assume you can actually estimate the disk of confusion, the R2 value CS alpha cube. Okay. So with using an optimum aperture, usually you can resolve in TM 0.2 nanometers apart points. Okay. This requires alphas to be very small. Fine. Now electron microscopes gain advantage of depth of, so then you can in the case of TEM, usually the depth of field is given by assuming is given by alpha square. So you can see that here the alpha, as you lower the alpha, R2 reduces, but as you lower the alpha, you can see that the R1 increases. So you have to choose an optimum value of alpha where you can get the minimum spherical aberration and with a good resolution. Okay. And in TM the H is given by 0.61 lambda by alpha square for electron microscopes. Okay. And as alpha reduces, you can see that H drastically increases. So you will have a very good depth of field in transmission electron microscopes. Okay. And these electrons can be easily scanned on the sample. That leads to we can use it for SEM, scanning electron microscope, to create the images, or SEM and BSc imaging, or in TM we can use this for STEM imaging, scanning transmission electron microscopes. Okay. So this is why we use the electrons for the imaging purposes. Fine. Now what we do is, the next part is how to generate an electron beam from the electron beam, correct. So first we need to understand the electron center interaction with the specimens. Okay. Usually a typical atom, you can see that there is a certain energy shells which are K, L and M. Okay. So these are very fundamental things which just to cover it, there will be inner shell electrons, lowest energy electrons near to the nucleus which are K and L, these are localized energies. There is a outer electrons, highest energy electron with the lowest binding energies, so these are called valence band, like outermost occupied shells, and there is a conduction band where they share the outer electrons with a range of possible energies, and these are delocalized. They are not they are delocalized. Okay. So for an electron which is at the outer shell or the conduction band, so a small amount of energy is needed to detach from the atoms from the outer electrons, correct. So this principle is used to remove the electrons and to use these electrons for the imaging purpose. As you know, in the nucleus we have a positive charge surrounded by negative electrons that neutralizes the charge, fine. And localized electrons in the outer electrons, these are shared depending on the type of bonding with the surrounding atoms. Okay. Now we know that an electron can behave as a particle or as a wave, and the electron has a charge of 1.6 into 10 - 19 coulombs and a very low mass of 9 into 10 - 31 per kg. Okay. And these electrons, if they exist, they show as a particle, these electrons can be accelerated through a potential difference of v volts, then its velocity v may approach the speed of light. So with this increase in the velocity, the electron mass will increase by this particular equation. Okay. M equal to me divided by 1 minus v by c whole square half. Okay. If you are considering as a wave, okay, so means it has a certain wavelength and also momentum, and it is related to a famous relationship which is called de Broglie relationship, and it is given by lambda, which is given by h by p, which is equals to h by mv. H is the Planck's constant. Okay. So the energy given to the electron can be equated to the energy represented by the change in mass between these two equations. Okay. So as I told you, as a wave, this is particular equation. So energy given to the electron can be equated by relativistic change of the mass, and by equating these two equations you will get EV equal to m minus MEC square. C is the speed of light, E is the charge, H is the Planck's constant, Ma is the mass of the electron, but mass of the electron when it approaches the speed of light, correct. Now with these equations, with these all three equations, you can actually calculate the wavelength as a function of accelerating voltage. Okay. If you solve this particular equation, you will get this particular last equation where lambda and voltage can be the lambda of the electron or the wavelength of the electron can be calculated by the voltage or the accelerating voltage. Here these are the values of typical a table, where you can see that with increasing the voltage or with increasing the potential or with increasing the acceleration with the voltage, the wavelength also reduces significantly while increasing the voltage, correct. So this is how we will get the different wavelength lambda, and these lambda you can see that these are in the nanometers. These are actually very small distances which are actually in relation to the interlamellar spacings of any unit cell. So these values, by using this electron with this wavelength, can actually resolve the interlamellar or interatomic distances. That is why we choose this lambda with a very low value. Fine. So with this introduction, what I will do is I will briefly go through the generation of beam of electrons, and this generation of beam of electrons is done by two methods. One is thermoionic emission source and another one is field emission source. We will come to the field emission later. Thermoionic source. First we will talk about the thermoionic source. This is the widespread use of thermoionic emissions for the heating element. So, it is exactly like a bulb, correct. Here what are the components are there? So, there is a filament here, okay. There is a Wehnert cup which is called W, and here there is a anode plates. These are called anode plates, anode plate, okay. Now, usually across this filament a small current is passed when there is no potential is applied, okay. So, before filament current is high. So, when you apply a voltage across the tip, and this is the anode plate, then what you are doing is you are extracting the electrons from this particular filament, and these are accelerated towards the column, okay. So, this is typically electron plate. So, anode plate, for extraction you are getting a positive potential and these are applied as a negative potential, okay. Remember in atom probe tomography we have just introduced that time. Actually you are applying a negative potential to the electrode so that you will extract the ions from the sample, correct. So, exactly similar thing you can assume that. So, there is a tungsten filament which is having some certain radius of curvature, and you are extracting, you are applying a very high potential at the anode so that it will extract the electrons from the tungsten filament. Now, if you are not applying any voltage, still there will be a small current which is passed towards the filament, and that particular current is called a dark current, okay. So, even though the electrons are not extracted from the filament, there is a current which is passed through the filament which is called a dark current. It means that it flows before it emits light, or it emits electrons, correct. So, if you see the electronic circuit design, this is your filament, it is applied with a Wehnert bias voltage, okay, and this is your anode plate where you are applying a positive potential, okay, and due to the application of this field, what will happen is you will generate a acceleration of these electrons. So, here you can see that the tungsten wire is a cathode which is a filament, and it is heated by passage of current to about 2800 Kelvin, okay. So, you are not applying a voltage, you are just heating this particular filament by passing the current across the filament. So, these are heated by passage of current to about 2800 Kelvin, and these are kept at a negative potential with respect to the anode, which is kept at a positive potential. And due to this positive potential, and if you increase the potential voltage, these will extract these electrons across the and accelerates towards the column, okay. So, the filament controls the diameter of the area at the end of the filament, and tungsten acts like, and Wehnert cup, this particular Wehnert cup which is a W, acts like a grid, okay. So, here the paths of the emitted electrons cross at one point in space, and that diameter depends on the area of the filament emitting the electrons, and this area is controlled by the potential between the filament and the grid RB, okay. So, you can see that these electrons are passed and they are concentrated to a particular spot, and this diameter depends upon the area of the filament emitting electrons, and usually this is the electron source. So the size of the electron source, and which is very important for resolution of a microscope. Here you can see that this is your beam current. Beam current means the actual electrons which are the current which is electrons are travelling after when you apply the potential, and this is your filament current. Okay. So the filament current increases initially. As the filament current increases, you can see that this particular value is a dark current, which is, as I told you, when you do not apply a voltage or a bias or a voltage, then this current passes through the filament. Now as you increase the filament current, you can see that your beam current increases significantly, but it reaches a saturation value which is called IC or IE, which is called a critical current, critical filament current. So there is not much change in the beam current, it almost gets flattens. So it means that there is no additional change in the beam current. Okay. So it means that it has a direct consequence on the brightness of the beam. So your brightness will not change after a particular critical current IC. So the B increases rapidly as your filament current increases. Okay. And also the brightness actually depends also upon the phi, which is called a work function. Okay. So brightness depends upon your temperature and the work function. Higher brightness means you should get higher temperature, so that you have to use a material or the metal which has a very high melting point, which is usually we call a tungsten. We are using it. It has a melting point of 3653 Kelvin, it is very high, and also the work function should be low enough. It is usually around 4.5 electron volts. It should be low, so that your electrons, the probability of the higher density of electrons can be removed very easily. So your brightness will be very high. So for a typical thermoionic emission with a tungsten wire, the brightness is around 10⁻⁹ am meter square stadian -1. Fine. So this is related to your brightness. So here I am showing you a typical image of a electron gun. That electron gun consists of it goes to a HT cable. You can see there are 2 points here, and in these 2 points there is a connected is the filament. Okay. So this is your filament, this is your Wehnert cup, and this is your anode plate, where you are applying a positive potential and it is negatively biased. Correct. So there are 3 major parts of the thermoionic gun from top to bottom. You can see that there is a cathode, this is your cathode, there is a Wehnert cylinder, and there is a anode which is shown separated here. So the Wehnert screws into the cathode, so you can attach this particular Wehnert cup or Wehnert cylinder to the cathode, and both are attached to the high voltage cable, which also contains power supplies for heating the cathode and biasing the Wehnert. The anode sits just below the Wehnert, and the whole assembly sits on the top of the column of the lens. So if you have seen any microscope, so there is a column and there is a panel and there is a screen here, correct, and usually the gun or the electron gun sits at this top region, okay, and this is connected to your HT cable. So here you can see a electric circuit where you can see that the filament, there is a bias resistor, there is a Wehnert cylinder, and there is a crossover which is controlled by the positive potential which is applied at the anode. Okay. And here there is a typical image of a filament with the two tips which is connected to a thin tungsten wire. As I told you, here we use tungsten as the source, thermoionic. So there is another source which is called a lab 6. The advantage of lab 6 is the work function is very low, it is lower as 3 electron volt. So you will get 10 times brighter by using tungsten. Okay. So the lab 6 filament also can be used for the as a source for the electrons. Now here there is a very good example of the effect of bias voltage on the acceleration of electrons towards the column. Okay. So you can see that this is your filament, and this is the Wehnert grid. You can assume this is a Wehnert grid and this is your anode. Now if there is no bias, then what will happen? There will be no deflection of electrons which are coming from the needle tip or the tungsten tip. So these electrons will flow as in this direction. So it has a long spread between these electrons. Okay. Here you will get the maximum current, but the beam will not be focused. So you cannot use this spreaded electron beam for your imaging purpose. However, if you put an optimum bias, you will get an intermediate current, but you will get a very fine spot by applying this voltage, so that these electrons will actually again deflected back to a certain point. This is called your what we call is a gun crossover. Okay. And but if you apply a very high bias, the electrons will not be able to reach the anode. Okay. So they will be deflected back. So you will not get any current, any beam current for the imaging purposes. Okay. So here you can see that the variation of the bias voltage versus the emission current. Okay. And you can see that at a certain region of the bias voltage, you will get the maximum brightness and maximum brightness. So your aim is to get not the maximum current or not the minimum current, your aim should be use the maximum brightness at a certain intermediate current, so that you will use these electron beam, focused electron beam, for the imaging purposes. Okay. So usually these electron beams, these electrons which are flowing from the filament are focused by using these biasing Wehnert grids. Okay. Okay, as I told you in thermoionic emissions, so this is the same, it is related to the brightness. So brightness definition is the beam current density per unit solid angle. So this particular solid angle is nothing but a steriden is the unit of a solid angle. What is steriden? It is the solid angle which encloses a surface on a sphere equal to the square of its radius. So this is a squareron. For thermoionic emissions, the brightness can be related to your voltage and the temperature and the work function. As I told you, the work function is and the temperature, both are very important for the high brightness, and these two depends upon your filament material. Okay. So in a layman language, we can say that brightness is a measure of how many electrons per second can be directed at a given area of the specimen. Okay. So this is generally related to a brightness. Now another, as I told you, there are two types of sources. One is thermoionic, another is field emission. What is field emission here? So here I can show you that so this is just an example of thermoionics. So this is your tungsten filament, lab 6, this is nothing but a crystal, lab 6 single crystal, where your work function is much lower, around 3 electron volt, your brightness is 10 times higher, correct. This is the difference between thermoionic emissions. Now there is another source which is called a field emission source. In the field emission source, there also use a very sharp tungsten tip. So the radius of the tip at the apex will be less than 50 or to 100 nanometers. A sharp tungsten tip is used, and usually the electrons are accelerated by generation of electric field. Remember when in the second class, when we started the introduction of the atom probe, I told about the two different aspects. So Professor Mueller, during his investigation, first he was working about the electrons, how to extract electrons by applying a positive potential to the anode and negative potential to the cathode, due to which he generates a very high amount of electric field which will extract these electrons. And as I told you, during in parallelly Ernst Ruska, he was also using these electrons for the designing microscope. So due to the de Broglie, due to the Heisenberg uncertainty principle, these electrons and they have a very low mass. So the uncertainty of electron to capture to a particular position is very difficult. That is why the resolution was for imaging, the resolution was very less than, it is almost not less than 2 nanometers. That is why the Professor Mueller went to reverse the potential with the negative and positive, so that you can use the ions for the field evaporation. Okay. So that is a different thing. Now here exactly in a similar way, if you apply a negative potential and a positive potential, then you will generate a very high amount of electric field, and due to this electric field, so there will be these electrons will be tunneled or quantum tunneled, correct. So we described about this process during atom probe also, but similarly here these electrons are removed from the sample specimen or the filament. Okay. So as I told you, here the field emission source, the metal or the source, usually it is a tungsten. The metal surface is subjected to extremely high electric field, which is greater than 10⁹ volt per meter, and due to which very high electric field, the probability for electron to leave the surface without needing to given the amount of energy for work function, it can tunnel very easily due to the presence of very high electric field. So here the temperature is not playing an important role, here the important role is played by the electric field. Okay. So here usually the more number of electrons can be drawn from the same area of tungsten. So your B increases up to 10⁻13, which is much larger than thermoionic sources, which is here around 10⁹9, correct. So it is almost 4 orders of magnitude larger brightness by using this field emission source, and this field emission source is nothing but the tunneling of electrons from the metal surface by using a high electric field near to the metal surface. Okay. So this is a typical equation where you can actually the field emission current depends strongly on the applied field, and EF is the Fermi energy which is 5 electron volt for tungsten at room temperature. Okay. So this is the density of electrons which can be removed in the field emission source. So this is a typical cross section of an electrical circuit, where you can see this is the field emission electron gun. It is, and it is nothing but the tip okay, and this tip is made very sharp in order to get a very high field strength with low voltages. Okay. The field emitting tip has a very strong curvature, means the needle specimen, the needle is around less than 50 nanometers, and this is done by etching a single crystal tungsten wire to a needle point, and it is less than 10 nanometers or it is up to 50 nanometers. Okay. The grid, similarly the grid will be there. There is a anode, there is a crossover. The grid provides the field that extracts the electrons by tunneling mechanism due to the generation of large amount of high degree of electric field near to the tip surface. Okay. So, there is a very small tip radius gives a very high field strength, which is 10⁻⁹ to 10⁻⁻⁻. Anode is positively charged, as I told you, so that it can extract the electrons, and its function is to accelerate the electrons to the at a potential. With this grid also you can generate a crossover, which is called a gun crossover, and your electron the energy spread in these is very minimal as compared to the thermoionic sources. Okay. So, thermoionic sources are heated up by passing a current, and there is a application of high voltage, so that the electrons will come out at high temperatures. So, usually you use a very high temperature source, high melting point source with a lower work function, but in the field emission you use the tunneling process by using the high electric field. Okay. So, with this I will end this class now, and I hope that you got a feeling about how the electrons are extracted from a metal surface. Usually the tungsten is used, and in the subsequent classes we will cover more topics related to the electron microscope. Thank you.